Limits at infinity and limits of sequences, lesson 3. So let's go ahead and take a look at the example. F of x equals x plus 1 over 2x. If I go ahead and I can see, say I try to graph it, and I get a picture that looks like this, if I were to graph this. So this is telling me that my limit as x is approaching negative infinity of f of x equals 1/2. And we can see that as I go further and further and further, I keep approaching this horizontal asymptote. And this horizontal asymptote is at 1/2. It's in between 0 and 1. And if I do that and I look at the limit as x approaches positive infinity, so now I'm looking at this part, it's going down, but it's still getting closer and closer and closer to this y equals 1/2 point. So the limits are getting arbitrarily closer to 1/2 as x decreases or increases without bound. So again, the limit for this, in this case, is going to be 1/2. So let's take a look at the definition of limits at infinity. So again, this is kind of what we just decided. The limit as x approaches negative infinity and the limit as x approaches positive infinity. You may get two different answers, or you may get the same answer like we did here. And then we also have the limit if r is a positive real number. So let's take a look at this example. Again, what does that mean? That means that as x is getting bigger, okay, my number is actually getting smaller. So again, think about that. If my denominator gets bigger, my number's getting smaller. 1/2 is, or 1/4 is smaller than 1/2. 1/10 is smaller than 1/4. 1/100th is smaller than 1/50th. 1/1000th is smaller than 100. 1/100. So as these numbers are getting smaller, again, your limit is getting closer and closer to 0 because the denominator gets bigger. Larger, let's say larger. So if you see this, that your denominator is increasing, again, whether it is towards the left side or towards the right side, your number is getting smaller and smaller, therefore it's getting closer and closer to 0. So let's do an example. So evaluating a limit at infinity. Find the limit. So we're going to say the limit as x approaches infinity, which is 4 minus 3 over x squared. So we're going to use our algebraic properties. Again, we can treat this type of equation in our parentheses as two separate terms. So I'm going to split this apart, and I'm going to say the limit as x approaches infinity of 4 minus the limit as x approaches infinity of 3 over x squared. So now we can, again, continue to simplify. So I'm going to take this first term, keep it exactly the same. Because I have this numerator here, I can pull this out front. So I'm going to rewrite this as minus 3 limit. I wrote 8 here. Should be a sideways 8. Limit as x approaches infinity of 1 over x squared. Again, I just pulled that 3 out front, and I should multiply it. Again, that 3 times 1 gives me 3. Now I can start simplifying. If I just have a constant, 4 is going to be 4, whether it's 2 or infinity. So the limit of 4 is 4. Minus 3, we just talked about when my denominator is increasing 1 over 10, 1 over 100, 1 over 1 million. That number is getting closer and closer to 0, so we say that this has a limit of 0. 4 minus 0, my limit is 4. So we would wrap up and say, to sum it up, the limit of f of x equals 4 minus 3 over x squared as x approaches infinity is 4. So that's kind of how you could summarize your solution. All right, we may have to compare limits at infinity. So let's take a look at a few examples real quick. We'll kind of buzz through these just so we can get to the comparing. Let's say that we have f of x equals negative 2x plus 3 over 3x squared plus 1. Let's do f of x equals negative 2x squared plus 3 over 3x squared plus 1. And finally, let's see here, do we have room to do over? I think we can maybe fit it in. We'll do almost the same, but all of these are slightly different. This one's going to be to a power of 3. All right, so let's start on the left. So again, if I try to split this up, or if I try to, I'm going to divide both the numerator and denominator by x squared, so I can kind of neutralize this. So again, let's think about it. Negative 2x plus 3 over 3x squared plus 1. And then these are all as the limit is approaching 0, so I should probably write that. The limit as x approaches infinity. So what we're going to do for our first step is we're going to multiply the top and the bottom by x squared, or excuse me, we are going to divide. So what I'm left with is the limit as x approaches infinity. X divided by x squared is just going to leave me with 1x here. And then this is still plus 3 over x squared. All over x squared divided by x squared is 3 plus 1 over x squared. Now again, we can identify, hey, my denominators are getting bigger. Therefore, if your denominators are increasing and your numerators aren't, you can assume that that is going to equal, that's going to equal a limit of 0. So this is going to be, if I substitute it in, 0 plus 0 over 3 plus 0. 0 over 3 equals 0. So the limit as x goes to infinity of this function, okay, it's just repeating what I started with, equals 0. All right, let's jump to this one. This one we're going to do basically the exact same thing. We're going to divide the numerator and the denominator by x squared. Limit as x approaches infinity. So why can you do this? Again, you have to look at your denominator can't equal 0. So what you want to do is divide each term by x squared. That's going to get this term right here to cancel out. That's kind of our goal. Why am I doing this? I'm doing it so that that x squared cancels out. And so we are left with negative 2 plus 3 over x squared all over 3x squared divided by x squared cancels out, plus 1 over x squared. Again, this is going to, as the limit goes to infinity, as our limit goes to infinity, that's going to eventually equal 0, which means we get an answer of negative 2/3. So the limit as x goes to infinity of what I started with, negative 2x squared plus 3, all over 3x squared plus 1 equals negative 2/3. Last example over here on the right. You can see it is a little tedious writing all of these out. But again, you got to show your work properly so that people will understand what you're trying to say. So same as we did in the other two, we're going to divide each term by x squared. So some stuff is going to cancel out. Therefore, we're going to get, this time we are actually left with an x in our numerator because it's a power of 3. 3 minus 2 is 1, so it's still there. Plus 3 over x squared all over 3 plus 1 over x squared. Again, notice these will have a limit of 0. But because we have this other x right here, we really can't conclude much because the numerator decreases with outbound as the denominator approaches 3. So again, this one would be an example of D and E does not exist because the numerator is going to just keep going because of this right here. Okay, we weren't able to cancel that out. So the limit does not exist. So to kind of summarize that right here. So if, again, looking at if n is smaller than m, you have a limit of 0. If n equals m, you have, which was our second example, you have a of n over b of m. And then if n is greater than m, again, looking at the degrees of exponents, green had a degree of 1. Blue had a degree of 2 on both the top and the bottom. And pink had a degree of 3 on the top and the 2 on the bottom, which is why the limit does not exist. So we did an example of all 3 kinds. Whoops. Lastly, for this first part, okay, I know it's getting a little long, we're going to find the average cost. I'm just going to take a picture of it so it'll be easier to get in here. So find the average cost. All right, greeting cards that cost 50 cents. Your initial investment is $5,000, which implies that you get this equation right here for your average cost, or for your cost. The average cost is shown by this. Again, add it up, divide by how many cards you make. Find the average cost when A is 1,000, or when X is 1,000, X is 10,000, and X is 100,000. What is the limit of C as X approaches infinity? So we can use direct substitution to start. So again, part A, X equals 1,000. So I'm just going to plug it in. 0.50, 1,000 plus 5,000 divided by 1,000. This gives me an average cost, when you simplify and plug it in, of $5.50. For B, X equals 10,000. So again, just plugging in my equation, just plugging it in right here. The average cost is going to be 0.50 times 10,000 plus my initial cost all over 10,000. And that's going to give me an answer of average cost of $1. Again, once you simplify it. And C, when I plug in X equals 100,000, I'm going to get an average cost plus 5,000 all over 100,000 of 50 cents. And so if we were to graph this, okay, if we were to graph this, we would see that our graph would look something like this. It would be decreasing Okay, and as I work all the way to 100,000, I'm going to end up with an asymptote in between 0 and 1, and that's going to be y equals 0.5. So as the limit approaches infinity, 0.50 x plus 5,000 divided by x. If I were to graph it and make my window really big and I see all the way to the right side, I see that I'm approaching 50 cents.